Welcome back to the last section of Chapter 4. This one we're going to be looking at row operations and augmented matrices. At this point, you should have some experience working with matrices in your calculator. Adding, subtracting, multiplying, finding the inverses and determinants, which makes what we've done so far this chapter much, much easier. Because the whole point of putting something into a matrix, stripping away all of the variables, all of the meaning, and just having numbers is so that technology, a computer, a calculator, can calculate those numbers for us. Because honestly, in the real world, a system of 3 by 3 equations is a very, very small system. People deal with huge systems that would be almost impossible to do without the use of technology and matrices. And so we're going to combine the technology and the matrices today. So our learning targets for today: I can use elementary row operations to solve systems of equations. Now we're going to spend a little bit of time on that, but not a ton, because we don't spend that much time on this topic. This is an introduction to matrices. Now, if you were in a year-long or even a semester-long linear algebra class, you would do a lot more of this stuff. But that is not the huge focus. We're going to see it so we can see what's going on, but that'll be about it. And then I can solve systems of equations using available technology. We are going to use these row operations to solve systems of equations. Now, in the past couple topics, we learned about Cramer's rule, which I can give you questions where you have to use Cramer's rule. You don't have enough information otherwise. I don't give you the system of equations, I only give you the determinants. We learned about how to do it using inverse matrices, where, alright, I can't force you to use inverse matrices to solve a system, but I can force you to use inverse matrices by decoding a coded message. This method I will not have to force you to use, because by the end of this topic, by the end of this lesson, this will be your preferred method of solving systems of equations. You may not believe me right now. You may think, you know what, I really like elimination. And good for you. Tell me that in a few minutes. So, for our row operations, the very first thing we want to look at is an augmented matrix. What is an augmented matrix? It's basically the coefficient matrix that you have been making already for the past couple chapters, with one little exception. So if we have a system of equations, we're going to get the coefficient matrix, this negative 1, 2, 3, negative 1, and we're going to augment it. We're going to add a column of our answers. So the augmented matrix is not a square matrix. We have 2 rows, 3 columns, and notice here we have our coefficients, here we have our answers. Sometimes these will be separated by a dotted line, sometimes they won't. The dotted line doesn't mean anything different, it's just there to separate, saying, hey, this is where the equal sign goes. If it's not there, you just have to know that that's where the equal sign goes. It can be there, it cannot be there, it doesn't matter. And so, that's an augmented matrix. We just take a system of equations and we make one matrix out of it. Instead of a matrix equation, instead of looking at determinants, we're just going to make one matrix. And then we're going to do some row operations. Now, we have a couple row operations that we will do. The first is we could multiply any row by a constant, as long as it's not 0. Just like we did when solving systems of equations. Notice this is just an equation. This is an equation. I can multiply this top row by 3. It's still going to be the same. Negative 3x plus 6y equals negative 3 is the exact same. We did that using elimination. In fact, the row operations is going to be very similar to the elimination method. So we can multiply by a constant. We can switch rows, because really, does it matter which order these equations are in? I could have put this 3x minus y equals 8 on top. Doesn't matter. So same thing, we can switch rows. You have to switch the whole row though. You cannot just switch the 3 and the -1. It has to be the whole thing. And we can also replace a row with the sum or difference of 2 rows. I could take row 1 plus row 2 and add it together and replace row 2 with that. That wouldn't get us much of anywhere, but I could do it. So I could make row 2, 2, 1, and 7, just by adding row 1 to it. Just like with elimination, we are going to be trying to eliminate the variables. We're going to be trying to get stuff to 0. And that process is called row reduction. And our goal is to get what's called reduced row echelon form. Now, that's a mouthful. A lot of times it's just abbreviated RREF. And what reduced row echelon form is we're going to have 1s in the main diagonal, 0s above and below it, and then a number out here past that main diagonal. And so, for instance, a 2 by 2 would look like this. We have 1s in the main diagonal, 0s everywhere else, and then just numbers here. And what this means is 1x equals a, 1y equals b. X equals a, y equals b. That sounds like a solution to an equation to me. A 3 by 3 would look like this. Notice we have a whole bunch of 1s, 0s above and below, and then numbers. So x equals a, y equals b, z equals c. And that's solved. So let's take a look at how we would use these row operations to solve this simple 2 by 2. So first, we want to make this number a 0. We could make this one a 1 first, but I kind of like that negative there for now. But let's make this a 0. How would we do that? We could multiply 3 times this first row and add it to the second row. And then we're going to replace the second row with that. So 3 times row 1 plus row 2, and it's going to go into row 2. So 3 times -1 is -3, plus 3 is 0. 6 plus -1 is 5, and -3 plus 8 is 5. So we replace the second row with this sum. Notice the top row stayed the same. Now, I want this number to be 1, not -1. So let's multiply the top row by -1, and then replace that top row with it. And so that'll just be 1, -2, +1. And the second row stayed the same. All right, well, now let's see. So we have 1 and 0. Now let's make this a 1. How can I turn the 5 into a 1? Subtract 4. How else can I turn the 5 into a 1? Thinking of these. Hey, multiply by a constant. Well, we can multiply by divide by 5. Well, what is multiplying by divide by 5? That's multiplying by 1/5. So we can take 1/5 R2 and replace row 2 with it. So that'll just be a 1 and a 1. And now we can use this 1 to make this into a 0. So if we multiply by 2 and add it to row 1, that'll be a 0. And we can replace row 1 with that. So we'll have 2 times row 2 plus row 1. So that'll be 0. 2 times 1 is 2 plus 1 is 3. So now this is reduced row echelon form. This first step, by the way, or the step above here, where we have the diagonals 1s and everything below it is 0s, this is called row echelon form. We want reduced row echelon form. It's way better. Because now we get 1x equals 3 and 1y equals 1. So x equals 3, y equals 1. And that's using the row operations. Now, it's, again, very, very similar to elimination. And with a 2 by 2, you're thinking, well, elimination's going to be easier than this. I don't get why that would be. With a 3 by 3, the two methods are going to be about the same. With a 4 by 4, it's going to be a lot easier to do it this way. But we have other ways. Because you're probably thinking, man, he said that this is going to be my preferred method of solving systems of equations. So far, I don't like it. Well, you got to give me another minute because we're not done yet. So let's look at how we really do this. Because remember our second learning objective, our learning target, is we can use technology to help us out here. So instead of just doing a 2-equation, 2-variable system, let's look at a 3x3. These are the ones that take a bit of work. So first of all, and this is going to be true anytime you put numbers into a matrix, we need to make sure everything's in the right spot, because we strip away all the meaning, all the variables, and the placement is the only thing telling us what that number means. And so, the first one's good. We have 2x minus y plus z equals 3. Second one, the z is on the wrong side of the equal sign. So we'll have to subtract the 2z over to get minus 2z equals 1. Here the x is on the wrong side, so we'll subtract the x over to get minus x plus z equals 2. And here I put a plus 0y here just to remind us not to forget about that 0. You don't have to put it there, but it can help save you mistakes every once in a while. And so now we can make our system of our matrix. So we're just going to pull the numbers out, the coefficients out. It equals 3, 1, 2, and we have a matrix. Fantastic. Next step, we're going to put this in our calculator. And so, using what we did last time, we can go to the matrix menu, so second, x negative 1. We can go over to edit. We're going to have a 3x4. So just enter your stuff into the 3x4 matrix. It'll take me a little while using a mouse. I apologize for that. But we're just entering our data. You should be able to keep up. If you have a calculator at home, I'd be following along. If you have to grab your calculator out of your bag or something, just pause and come back, because it's important to know where this stuff is. Almost done. Get our last column here. 3, 1, 2. All right, now I have it. We're going to quit out of here. Go back into the matrix menu. Now we're going to go over to the math one. This is where we have the determinant that you used last time. Here's augment. You can actually augment the matrix. I've never actually used that before because why bother? Just extend it when you're editing it. Then if we scroll down, REF, that's row echelon form. Here's reduced row echelon form, and then here's all the different things that we can do, all of our row operations. We don't care about those. We're going to reduced row echelon form, RREF. Plug in the name of the matrix, hit enter, and you're done. Look at that. 1, 1, 1, 1, 2, 3. That means x equals 1, y equals 2, z equals 3. Done. That was a lot easier than solving it by hand using elimination, wasn't it? So do you see what I mean when I say this will be your preferred method? So much easier. Now, to prove the point, let's get a blast from the past, shall we? Let's go back to section 3.6 and look at problem number 23. Now you might be thinking, let's see, 3.6 number 23. That was a couple weeks ago. I'm not sure if I remember that one. Let me refresh your memory. Oh yes, this one. This one that took up a full sheet of paper, took tons of frustration, probably way more time than you'd like, and you had to add a lot of quarters to that swear jar. But on the plus side, your dad's buying a brand new jet ski from it, so hey, it's not all bad. We're going to use a matrix for this. First, we're going to plug it into just an augmented matrix. Everything's in the right order, so we can pull the coefficients out, make a giant augmented matrix. And when I say giant, this actually isn't giant for a lot of what we use matrices for. For us it is, but not in general. And so we're going to plug this into the calculator. So we go back to the matrix menu, go over to edit. We're going to want a 4x5 matrix now. chances are you can type this in faster than I can using my mouse. If you can, you know what you're doing, go ahead. You can beat me to the answer. Because right now, it's dead air. So while this is typing, in order to find an inverse, yeah, we can just use the inverse button like we saw yesterday. To actually do it, like what it is actually doing, is you would make your matrix, your square matrix, and then you would augment it with the identity of the same size. Use row reduction, get you to the identity, and then the augmented part, the right-hand part, is actually your inverse. So I don't have it written down because you don't really need to use it now. If this was a bigger class, you would, but with what we're doing, you don't. But I just find that that's kind of a cool way of finding the inverses. Yeah, a cooler way is using this little button, but what does that actually do? All right, here we go. So we got everything entered. So we quit. We can go back to RREF. You can scroll down. I think it's actually faster to scroll up, but here we go. RREF, row reduced echelon form of matrix A. And ta-da! We solved it. Without using a full page, without swearing, without so much hassle. Isn't that magic? Right now you're probably swearing at me because I made you go through all that pain and suffering when there was a much easier way of doing it. Yeah, I did. Anyway, we have our matrix. So we have x equals 1, y equals -2, w equals 1, x equals -2, y equals -1, and z equals 3. And that is how we use technology to solve a system of equations using row reduced echelon form and row reduction. Have fun. I'll see you next time. Until then, happy mathing.